So hello everyone, this is lecture 8 for the classical physics. In that last lecture we discussed about this graph and we analyzed this graph. Okay, so this was the graph under a central force and we discussed, means we plotted the effective potential and here the distance, and then we analyze this complete graph on the basis of the energy at all the possible energies we have analyzed, and all the cases we discussed that where we will have the circular motion and where it will be elliptical or the where it will be unbound motion. Okay, so we discussed all the cases. Now let's see the application part, means let's see the questions, what kind of question can be asked from this. Okay, so it was very important here. When there was circular motion, then there was two kinds, the unstable and the stable kind. So there is this, I already told you, where it will be stable and where it will be unstable. So let's see the questions. A planet of mass m moves in a circular orbit, radius r0 is given, and potential is given minus k by r, where k is a positive constant. The orbital angular momentum of the planet is, so radius is given, means it is given that motion will be circular. Okay, so it is definite, and this potential is given, and we need to find the orbital angular momentum. So we know effective potential is this. Just remember this equation, it will be used in many questions. So it will be L square by 2m r square plus Vr. So Vr is given minus k by r. Now we know for the circular motion, this del effective divided by del r should be 0. So it should be 0 at radius r0. So let's differentiate it and place the value of r as r0. So this, now we can find the value of L from here. So it will be, L will be under root mk r0. Okay, so that's how you can find the value. So this will be your answer. Let's see next question. Two particles of identical mass move in a circular orbit under a central potential. Potential is given, let L1 and L2 be the angular momentum and R1 and R2 be the radii of the orbits respectively. And if L1 by L2 ratio is given, then we have to find the ratio of R1 divided by R2. So it is again given that motion is circular, so orbit circular, so definitely V effective, differentiation of V effective with respect to R will give us 0. So V effective will be this, and again find the derivative and put it equal to 0. Then you will get this equation. From here find the value of L square, it will be mkr4 and L will be this. So for L1 it will be under root mkr1 and for L2 it will be under root mkr2 square. So ratio will be this, and L1 by L2 is given, it is 2, so R1 by R2 will be under root 2. This will be your answer. Now let's see one more question. Consider a circular orbit. So just point this, that it is given that orbit is circular. In a central force potential is given where k is greater than 0 and n lies between 0 and 2. Time period of a circular orbit of radius r is t1. For radius r, time period is t1, and that of radius 2r is t2. For that circular orbit, if radius will be r, then time period will be t, and if radius is 2r, time period will be t2. So we need to find this ratio, t2 over t1. So how you can find? The same, first write the V effective potential, then differentiate it, equalize to 0. Find the value of L square or L. Then you know what is L. L is mr square theta dot. So for time period you need theta dot, because only the frequency can give you time period. So theta dot will be this, and theta dot is nothing but 2 pi divided by t. So t will be proportional to, this will go this side, so t will be proportional to this. So t2 over t1 will be r2 over r1 n by 2 plus 1. Okay, so from here r2 over r1 is nothing but 2r over r, so it will be 2. So this will be your answer. These are very easy questions, just you need to remember the basic concepts which I already told you, then questions will be very easy. These all questions are previous yearly questions from the GATE and the NET. So a planet of mass m and angular momentum L moves in a circular orbit in a potential this, where k is constant. If it is slightly perturbed radially, the angular frequency of radial oscillation is. So again this type of thing we already discussed, means a particle is rotating in a circular orbit, then we perturbed its energy, then it will go under oscillations, it will move like this. So it will have minimum radius and maximum radius. Now we have to find the frequency of this oscillation, this one, means with this oscillation it is rotating. So we need to find the frequency of that oscillation. So formula for that oscillation was nothing but second order derivative of V effective at r equal to r naught is radius at which it is circulating, divided by mass. So this will give you omega 1. So you have Vr, you can write V effective, then you will differentiate it 2 times, and for the first time you will get this equation, and from here you can get the r naught value. So this will give you the radius at which it will be rotating. Okay, r naught value, so it will be L square by mk from here. Now take the second order derivative and then put the value of r naught inside, and this will be r naught. So for r naught you will get this value of this, and divide by m you will get the frequency. So this will be your value of second order derivative. Now divide by m, you will get m square k4 L6, and under root of this will give you m k square divided by L3. So this will be your answer, the frequency. If they asked you the time period, you can write just 2 pi by t and you can find the time period also. Okay, let's see one more question. A particle of mass m carrying angular momentum L moves in a central potential this, where k and a are positive constants. The particle undergoes circular motion. What is the equation determining its radius r naught? So it's just simple, whatever we are doing, just the same. Vr is given, then you will put L square over 2mr square minus this Vr, you will get the V effective, differentiate it again and put equal to 0, and in place of r you will write r naught, then you will get the equation, and this will be your answer. This will be your answer, the equation for the r naught. Now let's see one more question. A particle of mass m having a non-zero circular momentum L is subjected to a central force potential. Potential is given k log r, where k is constant and magnitude of r is r. What is radius r at which it will have a circular orbit? Will the circular orbit will be stable or unstable? So we need to first find the radius, then we have to decide if it will be stable or unstable motion of the circular. So to find the radius, you will put d effective by dr is equal to 0. So from here you will get r equal to r naught, this will be this. So after solving you will get this value for the radius. Now how you can check if it will be stable or unstable? So if second order derivative is greater than 0, then you will have the minima in the curve. So minima is a stable point, and if you are getting less than 0, this value is less than 0, then you will get the maximum point, and this is unstable point. So let's check second order derivative, find the second order derivative of this, and then place the value of this r naught, and then you will get greater than 0, and that's why we will call that r naught. This radius is nothing but a stable circular orbit. Okay, so you can solve these. So that's why I skipped the steps, because they are all same. So let's see one more question. It's a little bit different, but just same. Magnitude of force between sun and earth is given by, force is given this time, not potential. If uniform distribution of dust in the solar system adds to gravitational attraction of the sun on the planet, with additional potential this, where m is mass of planet and k and c are constants, then period of circular orbit of radius r naught of the planet in the combined field is given by. So there was this force between sun and the earth, it was given, and there is this dust around the sun which is uniform, and there is this extra potential due to that dust, which can be represented by this. So now we need to find the period of the circular orbit of radius r naught around the sun of the planet, okay, by this combined field, by the sun and the dust. Okay, so if force is given, you can find the potential, because you know the relation, force is nothing but minus del v over del r. So del v is nothing but integration of this. So either you can do that, or there is this method. Effective potential will be L square by 2mr square plus Vr plus that extra potential. This will be your total potential. Now differentiate it, del v over del r, this, and this is nothing but, as I already told you, f is minus del v over del r. So del v over del r will be minus f. So minus f will be given by k over r square. So value of this will be k over r square. So now you have the whole equation, put equal to 0 for the circular orbit, and find the value of L. Means find the value of L, then substitute in place of L mr square theta dot, then you will get the theta dot will be this. Means from that equation you can find the theta dot, that will be equal to this, came out to be this. Okay, so from here you can find the time period, 2 pi over t, and t will be this reciprocal is this, and 2 pi. So these are very easy questions, just you need to remember the basic concept of this, and you can solve any question based on this. Now see, we were discussing about the orbits. So we are having the closed orbits and the open orbits, means unbound and the bound motions. So there we discussed that we are considering the polar coordinates, because the rotation was in a single plane, and in single plane if there is any bound motion, you can represent the motion by the r and theta components, okay, and or you can say in polar coordinates. So now you see that you need a equation which can relate r and theta, means at any point you can find the value, means if you are having theta you can find the value of r. So that relation will be called the equation of the orbit. So you need that equation. So how you can find that? There is this method. We know the central force is F equal to FR r cap. Now F is nothing but ma r fr fr. So this force is in the one dimension only, because it is like this. Central force will always towards or the away from the center of the source. That's why we can write this vector in this form, fr equal to fr. Okay, we don't need to place this vector here. So acceleration in the polar coordinates is nothing but r double dot minus r theta dot square. Just remember this as it is when we discuss the vectors in the in the mathematical physics. Then I will tell you how we get this. Okay, so for now just remember this. Acceleration is this in the polar coordinates equal to fr. Now multiply this mr double dot minus mr theta dot square fr. Now we need a equation here. See, this r is depending on time and this theta is depending on time, so we are having extra factor, that is time, and r and theta. So we need to remove that time variable from here, and we need a equation in this form where r is depending on theta, so at any theta you can find the r value. So we need a relation something like that. So let's see how we can find that relation. So let's substitute in place of 1 upon r we will write u, means u will be 1 upon r and r will be 1 upon u. Okay, so let's see. From this equation r dot will be dr by dt, this will be equal to, differentiate this, minus 1 upon u square du by dt you will get, and now multiply with d theta and divide with d theta, you will get du by d theta multiply d theta by dt. Okay, so this is nothing but theta dot, and from this equation for the angular momentum, this will be remain constant in throughout the motion of the particle around the source. So that's why we are considering this equation, and from here we can find the value of theta dot. This will be L over mr square, and 1 upon r square will give you u square. So that's why we are getting theta dot equal to this. Now substitute this here, then you will get the value for r dot, and this will be equal to this, minus L by m du by d theta. Now we need to find r double dot to substitute in that equation which we were solving. So it will be minus L by m d by dt du by d theta, just multiply and divide by d theta, and now take this d theta here. So what you will get, and take this dt here, d theta here. So you will get second order derivative of u with respect to theta, and here you will get d theta by dt. And you know the value of this is theta dot again, and theta dot is this value, L over mr square. So after substituting here L by mr square, you will get this 1 upon r square will convert to u. Okay, 1 upon u. So you will get this as the r double dot. So you are having a value of r double dot, and you know what is r. R is 1 upon u. So just substitute in this equation, and see what you will get. In place of theta dot square, you will write L over mr square, and square of L over mr square, means theta dot is this, square of this will give you L square u 4 m square. You will write that in place of this, and r will give you 1 upon u, and r double dot we already find. So just substitute all the values in this equation, then you will get this equation, m minus L square u square by m square d square u by d theta square minus m by u L square u 4 divided by m square equal to fr. Now see, from this equation you can take something common. This m will cancel out this 1 square, and this will cancel out 1 square. So it will give you, just take the common, L square u square by m. So here it will be u cancel out, 1 u will remaining. So you will get this equation. After rearranging this, you will get this equation. Now see, this equation is depending only u and theta. You are having only two variables. These are u and theta. This r can be written as 1 upon u again. Okay, so you are having only u and theta as your variable. So you are having this equation. This is called the equation of path, means orbit, equation of orbit, differential equation of orbit. So remember this equation, very important equation. Now let's see the use of this equation. Orbit of a particle question is given. This is a previous year question. Orbit of a particle of mass m moving in a central force is given by this. So orbit equation is given, where k is a constant. We need to find a law of force. So when orbit equation is given, we need to find this Fr. This is called the law of force. Okay. So let's see this. In place of r, write 1 upon u. So you will get u will be 1 upon k theta square. So you will get k u equal to this. Now you need to second order derivative of u. You will find, and in place of u, you will write just this, and just solve this equation then. So you will get du by theta is this, d square u by d theta square this, and now you will substitute in place of this. You will get this, and this will be 1 upon k theta square, because this is u, simply u, and u is 1 upon k theta square. In the right hand side you will get this. So in place of u we written k square 1 upon k theta square. So it was u in the downside, so you will get this equation, and this is f1 upon u. You can write it fr also. Now see, this theta square is nothing but r by k. So it can give you r square by 6k. So 6k over r square 1 upon r, and this r will came out, it will give you r4 and r cube there. So this will be reduced to this equation will be reduced to this equation. Fr will be this. So you are having your equation. This is depending on r only, and this is called the law of force. Okay. So there is one more kind of question can be framed from here, like you are having force. Now you need to find the potential. Okay. So how you can find? So you know what is potential. Del V over del R is equal to force minus del V over del R equal to force. So potential will be simply integration of this Fr minus integration of Fr dr. So this is potential, you know this. So L square over m, so minus will cancel out and you will get this equation. Now just integrate this 1 upon r4 and 1 upon r3, and you will get these as your, and this will be constant. So this will be your potential energy given by this. So you have your answer. Now one question was asked in the previous year. Let's see that question and relate with this question. A particle in 2D is found to trace an orbit r equal to r naught theta square. So it is something like same as r is equal to k theta square, only in place of k you are having r naught here. And if it is moving under a influence of central potential, and it was given that it is moving under this potential, c1 r minus a plus c2 r minus b, where r naught, c1, c2 are constant of appropriate dimension. We need to find the a and b values. Okay, so how you can find? So it's just same as we discussed the last question. So here we calculate this potential, and this came out to be this. And if you took this r to the numerator, it will get you will get r minus 3, and here you will get r minus 2. So just compare with this equation, r minus 3, r minus 2. So it will give you a equal to 3, b equal to 2. So value of a and b will be 2 and 3. So that's how a question can be solved. Okay, and this kind of questions are asked in the previous questions. So let's end today's lecture here. We'll meet you in the next lecture. We will discuss about the Kepler's law in the next lecture. Okay, thank you everyone.